Good afternoon, all of you. How are you, students? Yesterday we started colligative properties. Are all of you well? Doing well, all of you. See, last class we completed up to colligative properties. In that RLVP we discussed relative lowering of vapor pressure we did, and after that I taught you elevation in boiling point. Correct? So today our discussion will be on the same subtopic, that is colligative properties. In this colligative property, today we discuss depression in freezing point. That's what yesterday we discussed. The depression in freezing point is shown with the symbol del TF we discussed, correct? So on this subtopic we have to discuss depression in freezing point. So for that I have to teach you graph. See, draw a graph between, on the vapor pressure you take y-axis. Here you take Vp and here you take temperature. And if you remember in elevation in boiling point, the upper part will be solvent, the lower part will be solution we discussed. So this is for solvent and this plot is for solution, because see, vapor pressure is increasing with increase in temperature, and freezing point, see where this at this point what happens, see, this solid and liquid will exist in equilibrium. This is the point, freezing point for solvent. So this is T0 is freezing point for solvent, and this point will be freezing point of the solution. So in exam graphical approach they ask the point T0 will be freezing point of solvent, this is freezing point of solution. So and the difference between these two will give del TF. What is del TF? Depression in freezing point. This we are writing del TF. And this point, you remember, it will be equal to atmospheric pressure. And if you take a plot of this boiling point, if you remember, this will be boiling point of solvent and this will be boiling point of the solution. This difference will give elevation in boiling point, del TB. So understood, this in exam they may ask you by the graphical approach also what this point corresponds to, what this point is. See, solution, what is happening, freezing point of solution is getting decreased. Solvent is coming more, whereas boiling point, see, it is just opposite. Freezing point, boiling point of solution comes more. Boiling point of solution is less, and difference of these two will give del TB. Draw this graph. Clear, students, all of you? So this is what depression in freezing point. Yesterday we wrote a relation. Now adding solute to solvent, freezing point of solution gets lowered. This point where solid and liquid exist in equilibrium. This is for solvent. At this point, solid and liquid exist in equilibrium for solution. Done, students? Right. Now see, yesterday we discussed the cryoscopic constant. No, what is cryoscopic constant? Kf. And this cryoscopic constant value will be highest for camphor. I told you yesterday Kf depends only on the nature of solvent but not on nature of solute, correct? So which solvent will have highest cryoscopic constant means camphor. Make a note, camphor has highest cryoscopic constant. So camphor is widely used in order to determine the freezing point of the solution. So make a note, camphor has highest Kf value. Nearly 80 its value will be. And in NCRT there is one point mentioned during winter season. You remember the roads will be sprinkled with sodium chloride. Remember when during winter season what happens? Ice will be forming on the road, no? So to avoid the ice forming, what they do, they will sprinkle sodium chloride. So what sodium chloride does? Sodium chloride will decreases the freezing point and it will not allow ice to form. So conceptually they ask you during winter season, make a note. during winter season, roads are sprinkled with sodium chloride. What the purpose they sprinkle on the roads with sodium chloride means? Sodium chloride, you know, it is a salt. By adding the solute to the ice, what happens? It will not allow the ice to form. So sodium chloride, when during winter season, roads are sprinkled with sodium chloride to decrease the freezing point. To decrease the freezing point of ice. Understood, student? This point has been mentioned in NCRT. And one more important, in winter season, there is a compound called ethylene glycol. You study that in organic chemistry. So what is ethylene glycol, student? In first year, you studied in organic. Ethylene glycol, ethylene on oxidation with KMNO4. Remember, this is called ethylene glycol. Common name we call glycol. Ethylene glycol. IUPAC name you remember, we call ethane 1,2 diol. And this compound is used as antifreeze during winter season in car radiators. This is used as antifreeze. What for? It will not allow ice to form. Antifreeze in car radiators. So this is important in NCRT. What is that an antifreeze substance used in car radiators? Ethylene glycol. Understood, students? Are you revising? See, today is the last day for you. And I told you yesterday homework has been allotted for you up to solutions colligative properties. By today we will complete the colligative properties, and as soon as your holidays vacation is over, from June 1st you have to submit the homework up to colligative properties. Understood, Amma? So for you homework will be shared to you starting from introduction of solution chapter to colligative property will be having for homework. Day wise we have given homework. That when after completion of vacation you have to submit that homework in your notebook. Okay, clear? So copy this one. Ethylene glycol is used as antifreeze in car radiators during winter season. As an antifreeze, what it does, it will not allow ice to form. Now write one question related on depression in freezing point. A question you write. 0.5 grams of urea. What is the formula of urea? It's a non-volatile solute. NH2CONH2 is added to 100 grams of solvent, water. Its Kf value. What is Kf, student? Cryoscopic constant value is 1.86 Kelvin kg per mole. Then find the freezing point of the solution. Now go through this question. Understand the question what I am saying here. 0.5 grams of urea has been added to 100 grams of water, and its cryoscopic constant. Yesterday we discussed cryoscopic constant will be fixed for a given solvent. This is for water given, and he wants to find the freezing point of the solution. Now yesterday what is the relation, student? If you have recapped the concept, we wrote a relation yesterday del TF, that is depression in freezing point is given by Kf into m we wrote, correct, where m is molality. Now this depression in freezing point you have to be careful, difference of solvent minus solution we have to take. Freezing point of solvent minus freezing point of solution, this will be expanded as Kf into small w, mass of solute by molar mass of solute into 1000 by weight of solvent. Correct? This is what yesterday we wrote the relation. But here freezing point of solvent as it is water, what we take? Water freezes at 0 degree Celsius. So in place of T naught, you substitute 0, and freezing point of solution we have to find. This is unknown, no? That's what in the question is asking. And Kf value will be given in the problem. This is constant 1.86 Kelvin kg per mole. So substitute 1.86. Mass is given 0.5 grams into weight of solvent is given in grams by molar mass of urea. Urea, what is the molar mass? When you find algebraic sum of atomic masses, that comes 60 into weight of solvent given 100 grams. So this you cancel, 0, 0 get cancelled, this cancels, this will come how much? See, this one 60, 2 3s are 2.93, and this can be cancelled 10 times, 3 ones are 3 3s are 1s are. Correct, and 10 will be remaining. This I can cancel 0.1 by 2. That is nothing but 31. You write decimal after how many digits? 2, 3 digits. That is 0.031 by 2. And on simplification, this can cancel by 0.02. Ones are 2, 2 5s are 10. So nearly 0.015 we get. That means 0 minus Ts is coming how much? 0.015, this much in degree Celsius. So this is the value we got, but this is not the freezing point of solution. Now freezing point of solution, when you bring what you get, minus when you bring that side, minus of 0.015 degrees Celsius. This will be the freezing point of the solution. See what happened to the freezing point of solution, has it been decreased or not? So 0.015. Initially what is the freezing point of solvent? 0 degree, but 0 degree went to how much? Minus 0.015 degree Celsius. This is the freezing point of solution. Understood? Direct substitution. So in the problem, mass of solute will be given, weight of solvent will be given, and cryoscopic constant is constant for water. Yesterday we discussed that 1.86. Substitute that and simplify. Check, answer is coming 0.015. Unit will be in what? Degree Celsius. Understood, student? This is what depression in freezing point. So in the exam you get numericals on this. You have to put practice the questions from PW assignment you have to solve for coming homework next when you come on June. So copy this answer is coming minus 0.015 degrees Celsius. Clear? No doubt, no, right? Now with this colligative property, relative lowering of vapor pressure we done, elevation in boiling point we did, and depression in freezing point we did. What is the last colligative property? Osmotic pressure. Right, heading osmotic pressure. Right, next heading osmotic pressure. Right, osmotic pressure. This is the fourth colligative property in solutions we are having. Osmotic pressure, now onwards we show with the symbol pi. This is the symbol for osmotic pressure, pi, or we also call it as hydrostatic pressure. What is meant by hydrostatic? The water is exerting pressure. This osmotic pressure is also called hydrostatic pressure. What is that we discussing now? Hydrostatic pressure we say. Hydrostatic pressure. Now let us, before going to this osmotic pressure or hydrostatic pressure, you have to know some terms like osmosis. Some concepts before going to osmotic pressure. We have to discuss some concepts like osmosis. Right, heading osmosis. Now see what is this osmosis? Might be you do if you see this in daily life during rainy season. When water falls on the wooden door, after some days what happens? The wooden will bulge. Is it right? Anyone has been observed that in daily life? So what happens? Water gets inside the door and it gets slowly what bulge. So osmosis is nothing but see in you can see one here. I am taking one beaker. In the beaker, I am taking one thistle funnel. See, I am taking one. What is the name of this funnel? Thistle funnel. I am saying. See, this is thistle funnel. We call spelling THISTLE. Thistle funnel. Inside this thistle funnel, I am taking sugar solution. See, inside this thistle funnel, inside I am filling with water, sugar solution I am filling. This is yellow color is water, sugar solution. This is of sugar solution. And this thistle funnel, below to this thistle funnel, we are it is having one semi-permeable layer. This is semi-permeable, SPM we say. What is SPM means? Semi-permeable membrane. Semi-permeable membrane. Understood? The thistle funnel is fitted bottom semi-permeable membrane, and this entire thistle funnel which is filled with sugar solution, this is kept in water. See, this thistle funnel has been kept in where water it is kept. Like this, imagine this white color what I am showing is water. This is water I kept. Now slowly what happens, imagine students, when we are placing the thistle funnel filled with sugar solution, can you guess what happens? Might be you know this slowly the water molecules will get inside the thistle funnel. Do you agree? See, slowly what molecules are moving into the thistle funnel? Solvent molecules are moving. So only semi-permeable membrane will allow only solvent molecules to pass but not solute particles. Getting my point? So what happens to level of this slowly the level of sugar solution increasing to certain extent. Up to this understood? Now what we define for osmosis? Simple. Osmosis is movement of solvent molecules from lower concentration to higher concentration through semi-permeable membrane. So imagine this sugar solution I am calling as C2. The sugar solution, assume its concentration is C2 and water concentration, assume it as C1. And assume here concentration of C1 is less than concentration of C2. That means here water is not having any solute, no? So its concentration is less, whereas this is having more concentration. So hence what we define for osmosis is simple. The movement of solvent molecules from lower concentration to higher concentration through semi-permeable membrane, and that process is called osmosis. Understood, students? So write definition of osmosis. Movement of solvent molecules from where to where? From lower concentration to higher concentration through what membrane? Semi-permeable membrane. What is that membrane, students? Through, I abbreviate with SPM. But you people write total SPM means a semi-permeable membrane is known as osmosis. So understood, simple concept of osmosis is nothing but movement of solvent molecules. So in exam conceptually also they ask solvent molecules are moving from where to where? Lower concentration to higher concentration through water semi-permeable membrane. And that process is called osmosis. Clear, student? Now let us see what is SPM. What is SPM? SPM means what? Semi-permeable membrane. Right here SPM full form is semi-permeable membrane. Now what is the role of semi-permeable membrane? Say a membrane that allows only solvent molecules to pass through it but not solute. So what is the role of semi-permeable membrane? It will allow only solvent molecules to pass but not a solute particle, and that is called semi-permeable membrane. Example, you know, on the egg there will be a membrane, egg membrane, might be you saw on the egg layer will be there, and you know parchment paper, cellophane paper. Those are all what natural semi-permeable membrane, egg membrane, pig's bladder, as well as parchment paper we use as SPM. So make right definition: a membrane that allows only that allows only solvent molecules to pass, and such membrane what we call a semi-permeable membrane. Then what are the examples for semi-permeable membrane naturally available? If they ask, right here, egg membrane. See, on the egg layer, I am writing an example for semi-permeable membrane here. SPM egg membrane, as well as what? Parchment paper, spelling parchment, Parachment, and cellophane. These are all natural semi-permeable membrane. And in NCRT, one synthetic semi-permeable membrane mentioned. What is that synthetic? I write here, see. Synthetic semi-permeable membrane is synthetic, that is man-made synthetic we say. Synthetic semi-permeable membrane, SPM I abbreviate. This is Fe4 FeCN taken 6. Ferric ferrocyanide, not cupric ferrocyanide, it's cupric. What is the formula for cupric? Cu2. Sorry, cupric ferrocyanide, Cu2, right here, Cu2 FeCN taken 6. This is the synthetic semi-permeable membrane. You have to remember which acts as a semi-permeable membrane. This is synthetic cupric ferrocyanide. Later we study coordination compound. Right name of this compound, cupric ferrocyanide, and these are all what? Natural semi-permeable membrane. What are those? Egg membrane, parchment paper, cellophane, these are all natural. So understood students, just now what we learned, what is osmosis we learned, and what is semi-permeable membrane, and what are the examples for semi-permeable membrane we learned. Clear? Copy डाला. Now next our discussion will be on osmotic prayer. Now let us see what is osmotic prayer. Now simple, see, observe here carefully. As osmosis proceeds, what happens as osmosis is happening? What is the level of water inside the chisel funnel happens? Slowly level of water increases, no? And what happens? It will exert some pressure on it. The level of water inside, when the sugar solution inside the solvent molecule is entering, no? So it will exert pressure, and that pressure we are calling osmotic pressure. Means what is that pressure we are calling? Hydrostatic. The pressure exerted by solvent molecules. That means what we define for osmotic pressure? The external pressure or the pressure exerted on the solution. This pressure what we are calling HDG, that is height into density into gravitational force. The pressure exerted by the solution to prevent what? Osmosis. Now this is not allowing further any solvent to pass through it, and that pressure we are calling as what? Osmotic pressure. So what we define for osmotic pressure? The pressure exerted by the solution, where that solution is inside this chisel funnel, no? So the pressure exerted by the solution which prevents the passage of what? Solvent molecules to enter into solution, and that pressure we are calling it as what? Osmotic pressure. Understood students? So simple. Osmotic pressure is nothing but the pressure exerted by the solution. On what it is exerting? On the solution. After certain time, as solvent molecules are moving inside the chisel funnel, it is exerting the pressure on the solution, and it will not allow the passage of what? Solvent molecule further to enter into it. and that pressure we are calling it as what? Osmotic pressure. Understood all of you? Clear? So right definition of osmotic pressure. Right, osmotic pressure, what we define, right definition, or what is the other name for osmotic pressure, student? Hydrostatic pressure, no? This is shown with the symbol of what? Pi, or hydrostatic pressure we say. Now right definition, what we define for osmotic pressure, the pressure exerted by the solution, the external pressure or hydrostatic pressure exerted on where, students? On solution, no? On solution to prevent what? Osmosis. To prevent, in one word I am saying osmosis. Osmosis, you are familiar, no? Movement of solvent into solution is known as what? Osmotic pressure. And that we are showing with the symbol of what? Pi. Clear, understood? Hydrostatic pressure is also called osmotic pressure. Osmotic pressure is nothing but the pressure exerted by the solution. In the sugar solution, the pressure is exerted that will not allow further solvent molecules to pass. And that pressure we are calling osmotic pressure or hydrostatic pressure. And which is shown as pi is equal to height into density into G, gravitational force, HdG we say. Up to this clear all of you? No doubt, no? Now observe here. This osmotic pressure, tell me students, how it is related with concentration. So do you agree, more is the concentration of solution, higher will be the osmotic pressure? If the concentration of the solution is increasing, what happens? Osmotic pressure also increases, no? Hence, we can correlate osmotic pressure is directly proportional to concentration. So, higher is the concentration of the solution, higher will be the osmotic pressure, keeping temperature constant. Copy that relation where pi is osmotic pressure, C is what? Concentration. Understood? Where pi is osmotic pressure, C is the concentration. Means as concentration increases, what happens to osmotic pressure? Osmotic pressure of the solution increases. And you know, from Boyle's law, Charles' law, we can write one ideal gas equation. So from this relation, when you remove the proportionality, we write a relation pi is equal to C into R into T. This is the relation. On removing the proportionality, we are multiplying with a R. What it is R called? Solution constant. This is called a solution constant. What is R? R is called universal gas constant. You studied in states of matter in first year. This is called solution constant. Its value is same as R value. Remember in 11 states of matter 0.0821. Its unit will be liter atmosphere. Atmosphere, PV is equal to nRT, no, atmosphere per liter. So this is the value of R. As you know, PV is equal to nRT, you remember. So R can be written what, student? PV by RT, no. So its unit will be atmosphere liter per mole. R is equal to PV by T. When you bring from this PV is equal to nRT, R what we write relation? R is equal to PV by NT. For 1 mole of the gas, what we write? Atmosphere liter per mole for the given constant temperature. So its unit will be atmosphere per liter per mole. This is the value of R, solution constant. In this relation, we get numerical, where pi is osmotic pressure, C is concentration, R is solution constant, T is the temperature, keeping temperature water constant. The second, Boyle's law, Charles' law, Avogadro's law, on combination of those 3 laws, we bring this relation pi is equal to CRT, where C is concentration, R is solution constant, T is the temperature. Copied all of it. Understood? So this is what osmotic pressure. Now see what we write in this. Phi is equal to CRT we wrote no. Now C can be written what, students? As you know, in mole concept, molarity is nothing but number of moles per unit volume, no? Concentration is what? Number of moles per unit volume. So we can further write this as what? Phi is equal to N by V into R into T. Where N is what? Number of moles, V is what? Volume of solution in liter, R is universal gas constant, T is temperature. Further moles, what we write, student? Mole concept you are familiar, no? Mass by molar mass. This can be further expanded as what? Pi is equal to mass of solute by molar mass of solute into R into T upon what? V. This is an important relation. We get numericals in JEE mains as well as in NEET. So in the problem they give you mass of solute to you and volume of the solution. If it is not in liter, you have to convert it in liter, and temperature will be given. R value, if it is in atmosphere, you have to take R value 0.0821. What is the unit? Liter atmosphere per mole per Kelvin. This will be the unit. M is what? Molar mass. V is volume of solution in liter. This is important relation. Understood, student? This is osmotic pressure. So make a note where W is mass of solute, M is molar mass, R is solution constant, T is temperature, V is volume of solution in liter. Clear, students? Now write one question on osmotic pressure. Numerical you write on that osmotic pressure. Find the osmotic pressure of 0.1 molar sucrose solution at 27 degrees Celsius. Now see, question understood what we have to find. Osmotic pressure he wants to find, and concentration given to you 0.1 molar at temperature given 27 degrees Celsius. So concentration we know, we have to find pi. Then what is the relation for osmotic pressure? Pi is equal to CRT, where C is what? Concentration, and R value what we take. So 0.1 is the concentration, R value 0.0821. Temperature, convert this to 27 degree in Kelvin. That is 27 plus 273 comes how much? 300 Kelvin. So multiply this with 300 and multiply 821 with 3. 821 3s are 1 3s are 3, 6, 2, 4. 2463. Is it coming 2463? And 2 zeros are there. Put decimal after 5 digits. So when you place decimal after 5 digits, see, understood, 5 digits you place 3, 4, 5. Answer you have to get nearly 2.46 in ATM. What is ATM? Atmosphere. This will be the osmotic pressure. Understood, symbol? So osmotic pressure, he has given concentration to you, temperature given. Direct relation, phi is equal to CRT, where C is the concentration, R value is solution constant, its value is constant 0.0821. Provided if it is in atmosphere. So if the option is given in atmosphere, temperature you have to convert in Kelvin. Clear up here? Now write next heading, isotonic solution. Next write heading, isotonic. Now this is important in exam point of view. They are asking questions from isotonic solutions. Now see, what are isotonic solutions? Solutions whose concentration remains same. Iso means what, student? Same. Tonic means what? Concentration. So solutions whose concentrations are same, such solutions what we call isotonic solutions. Understood? So write definition. Isotonic means what? Solutions whose osmotic pressure whose concentration remains the same at a given temperature. Such solution what we call isotonic solution. Understood? Iso means what? Same. Tonic means concentration. No? Clear up here? Now see students, we wrote one relation here in osmotic pressure. How is osmotic pressure related to concentration we wrote just now? It is directly proportional to concentration we wrote, no? So since we are defining solutions whose osmotic pressures are same are called isotonic, we are defining. So if concentration is remaining same means how will be the osmotic pressure of the two solutions? If concentrations are same means as concentration is directly proportional to osmotic pressure, no? So can I say the osmotic pressure of the solutions will also remain same or not? Hence what we can say that for two solutions I can say osmotic pressures can also be equal or not? Osmotic pressure of the two solutions will also be same, correct? Are you getting my point? So as concentrations are same, as osmotic pressure is directly proportional to concentration, so osmotic pressure of the two solutions will also remain same, no? So this is what the relation for isotonic solution. And we wrote a relation C. Can I write this as C1 value will be equal to C2? Correct? And C1 can be written what, students? Concentration is number of moles per unit volume, no? So I can write N1 by V1 is equal to N2 by V2 because concentration is nothing but number of moles per unit volume, no? And this can be further written what? Mass by molar mass. W1 by M1 V1 is equal to W2 by M2 V2. This is another important relation. In this relation, they may ask questions on isotonic. Copy this relation where W1 is mass of first substance by molar mass of the first substance. V1 is volume of first substance. W2 is the weight of the second substance. Molar mass of the second substance into volume of the second substance. Understood, Rama? All of you. This is what the relation for isotonic solution. And in NCRT, in hospitals they give intravenous injection. Intravenous injection will be given by doctor. Why? Because our blood is isotonic with saline. The saline will be given no, for intravenous. So our blood, human blood is isotonic. So important in NCRT, if you remember, this human blood is isotonic with our blood is isotonic with 9.095% saline. That is 0.59% saline means what? NaCl. What does 0.95% mean? You studied no mass percentage. 0.95 grams of saline present in 100 ml of solution. Sometimes they may ask you in terms of molarity. You are familiar, no? In the introduction we did molarity related problems. So what does it mean? 0.95 grams of sodium chloride is been present in 100 ml of solution. That is what we are calling saline solution. Understood, students? So this is important, right? That blood is isotonic with 0.95% of saline. And this relation is important, put star mark. Here are you following? So till now what is osmosis we learned, what is osmotic pressure we learned, and next we have discussion we discussed on isotonic solution. Now write one question on isotonic. In this relation isotonic, write one question. See in exam point of how they ask on isotonic solution, right, 5% urea solution is isotonic with 10% of unknown substance. 10% of unknown substance X. We don't know what is that unknown substance X, and we have to find the molar mass of that unknown substance. Then find the molar mass, that is molecular mass of unknown substance X. Now question understand what I am given. See 5% of urea is there. is giving one hint. It is isotonic, is saying. Isotonic means what? Whose osmotic pressures are same with one 10% unknown substance. We don't know what is that unknown. Some unknown substance, it is always isotonic. And we have to find what will be the molar mass of that unknown substance X. Now, tell me how you done, all of you. So, how you approach this one? Since osmotic pressures are same, what you do, phi of urea is equal with phi of unknown X. So, as osmotic pressures are same, what we can correlate? We can correlate with urea of concentration of urea will be equal to concentration of X. Correct? And this can be written in the same relation, weight of urea by molar mass of urea into volume of urea. Understood how we got this relation? W by M1 V1 is equal to weight of unknown substance X by molar mass of unknown substance into volume of X. Now in the data, mass of urea given to you 5% means what? 5 grams is present in 100 grams, 100 ml of solution. So here I write 5 by, what is the molar mass of urea? 60. You are familiar, no? 11th, you are familiar. Molar mass is NH2CO, NH2, algebraic sum. That comes 60. And volume I have to take 100 because it is present in 100 ml of solution. This is isotonic with 10% is saying. What does it mean? 10 grams is present in 100 ml. So 10 by molar mass we don't know, unknown, into 100. Correct. Now what if we can cancel? 100 get cancelled. This 5 will cancel 10 by 2 times. Now find out molar mass of X. Molar mass of X, multiply this 60 with 2. That comes how much, students? 120. 120 in unified mass. This will be the molar mass of that unknown substance X. Understood symbol. So this is what isotonic in NCRT. They are asking questions in JEE mains as well as in NEET. We get isotonic solution. Understood the concept? Isotonic means whose concentrations are same, which when we can correlate with their osmotic pressure. Following students, all of you. Now lastly, right, reverse osmosis. Last concept for today. Copied all of you, understood all of you, this numerical, clear, no? Right. Now write next heading, reverse osmosis. Now what is this reverse osmosis? Might be observed in daily life, in corporate colleges and in corporate hospitals. They will mention RO. RO is what? A reverse osmosis. Just opposite to osmosis. Osmosis, what we learned? Movement of solvent from lower concentration to higher concentration we learned, no? But here it is reverse. Movement of solvent from higher concentration to lower concentration. That is what you see in, what do we say, river water. The river water is made potable water. Potable means what? Drinking water by the same reverse osmosis. How? See, let us draw this diagram. Imagine this is one plant I took. Here I made two partitions here. Here two partitions I am making, and here one piston I am placing here, and in this I have took sea water. This is of sea water, and this I am placing one outlet here. This is for pure water. This is of pure water. Getting idea? This is pure water, student, and here it is water, saline water. That is sea water. It is. Understood all of you? This is the diagram. Now see what is reverse osmosis. Simple. Here we are placing one piston. See, had you saw this? This is the piston on the surface, on the top of this saline water. And what we are doing, we are exerting pressure there. So here one external pressure is applied. P external we call. See, this is P external. Now this P external, what we are doing, we are pressing external pressure. And this external pressure we are applying greater than osmotic pressure. So understood, an external pressure is higher. What is osmotic pressure? The pressure exerted by the solution to prevent osmosis, we learned, no? So the external pressure what we are applying on this, it is higher than the osmotic pressure. When you are applying external pressure higher than osmotic pressure, what happens is, instead of moving solvent into solution, the solvent present in solution will move reversely. Getting idea? So what is happening? The water present in the sea water, pure water will go into this and we get water, potable water here. So in exam conceptual they ask you how should be the external pressure compared with osmotic pressure. In reverse osmosis, the external pressure applied on the sea water should be higher than osmotic pressure. Then only what happens? Solvent molecules from solution will pass into pure water. Hence what we define here, right definition, an external pressure applied on solution. An external pressure applied on solution is greater than what? If it is greater than, osmotic pressure, I abbreviate with pi, then reverse osmosis takes place. Understood, student? Reverse osmosis just opposite to what we learned for osmosis. That means the external pressure, how it should be, they ask in exam. This is important. External pressure should be higher than what? Osmotic pressure. And what is this reverse osmosis is meant for me? To convert the sea water into potable water. So here, right, sea water can be made to potable water. Potable is what? Drinking water. Conceptual based, so they can ask the reverse osmosis. Clear? So with this all colligative properties we completed. What are those four? RLVP, relative lowering of vapor pressure, osmotic pressure, elevation in boiling point, depression in freezing point. So today, once you recap all these concepts from the introduction, and those who not attended the class, you copy notes of from your friends. And I told you, no, from tomorrow onwards you don't have any class, but homework you have to do daily basis. We will share the homework for you. And when once you join on June 1st or 2nd or what else the date it may be, on that day you have to submit the homework. From PW questions you have to solve, DPP as well as from PYQ. The concept till the concepts of colligative properties. Not all, till the concepts what we discussed in the class. That is types of solution, after that concentration terms, Henry's law, solubility of solid in liquid, solubility of gas in liquid, then vapor pressure, boiling point, vapor pressure of liquid in liquid, vapor pressure of solid in liquid, and after that we discussed deviation, positive deviation, negative deviation, azeotropic mixture, and colligative properties of 4 RLVP, osmotic pressure, elevation in boiling point, depression in freezing point. Till this syllabus, I have to solve questions for the coming next vacation holidays. Day wise we have allotted the work. See that will be shared to you. So all the best. I am ending the session. Bye.